Okay, let's have a look at the solutions for these. Most of them weren't too difficult. If you could see the little trick that would help to simplify it. So we'll go through those now. Okay, so number one. Okay, so number one, this was straightforward to do, no tricks for this one. So we have the integral from 2 to 3, 8x cubed plus 3x squared plus 6x dx. Okay, I saw a few of you are not writing the dx on the end here. Please make sure that you include all the notation for these. Okay, if you don't put the dx at the end, I'm going to be deducting marks. Okay, so to find the antiderivative, we add 1 to the exponent and divide. Okay, so it's just a normal polynomial. So we're going to have 8 over 4x to the 4 plus 3 over 3x cubed plus 6 over 2x squared from 2 to 3. This simplifies, so 8 over 4, that will be 2, and then we have 3 cubed. 3 over 3, that's 1, so it's just 3 to the 4. 3 to the 4, that will be 3 cubed. 6 over 2, that's 3, and then we have 3 squared. And then minus, and then we substitute the lower bound, so that will be 8 over 4 again, that's 2. 2 to the 4, plus 2 cubed, plus 3, and then we have 2 squared. Okay. And then after this point, it's just putting in your calculator, so I won't be doing that. But if you got the antiderivative correct and you got the substitution correct, then you'll get the final answer correct. Okay, you have your calculator, so that shouldn't be an issue. Okay, let's have a look at the next one, number 2. Okay, so here there was a little trick, not too difficult. So cos squared x dx. So here we can't find the antiderivative directly because it's cos squared. If it was cos or if it was sine, then we could do it nicely. But the way to go is to turn the cos squared into something with either cos or sine. So for this one, we're going to use that double angle formula. So here we can write this as the integral from 0 to pi, 1/2 1 plus cos 2x. Okay, so now instead of writing it as cos squared, we've just got cos by itself. Okay, so it's easier to work with. If that was sine squared, then we would replace the plus with the minus. Okay, so the sine squared and the cos squared are almost the same, except the plus in the middle there changes to a minus. Okay, so here we can write this as the integral from 0 to pi, 1/2 plus 1/2 cos 2x dx. And now we can find the antiderivative quite easily. So this will be 1/2 x plus 1/4 sine 2x from 0 to pi. Okay. Remember, when we're finding the antiderivative of cos ax, we need to divide by the a, not multiply. So when we differentiate, we multiply by whatever's in front of the x. Here we need to divide. And remember, the antiderivative of cos is positive sine, because the derivative of sine is positive cos. Okay, it goes back and forth like that. Okay, then we can substitute. So we're going to have 1/2 pi plus 1/4 sine 2 pi. If we substitute 0, we're going to get 0 plus 0, so that doesn't do anything. Also, sine of 2 pi is 0, so that can go, and we're just left with pi over 2. Okay, so remember your bounds for the trig functions. Cos, if you're looking at cos of 0 or cos of 2 pi, that's going to be 1. Sine at 0, sine at pi, sine at 2 pi, all of those are 0. Okay, if you just remember that, then you don't need to worry about using your calculator. Okay, next one, number 3. So we have the integral from 1 to 4, root x plus 3x dx. Okay, so if we have the root x, we need to change it to an exponent. So this will be the integral from 1 to 4, x to the 1/2 plus 3x dx. Okay, now we've got it in that exponent form. We just add 1 and then divide as usual. So adding 1 will make it 3 over 2, dividing will make it 2 over 3. So 2 over 3 x to the 3 over 2 plus 3 over 2 x squared from 1 to 4. We substitute the top number, so it will be 2 over 3, 4 to the 3 over 2 plus 3 over 2, 4 squared, minus, and then in brackets we substitute the bottom number, so it will be 2 over 3 plus 3 over 2, and then from this point it's just some work with the fractions. Okay, so I won't go through that with you, but it's quite simple to go through. Okay, any questions so far with these ones? Okay, number 4. Okay, we have the integral from minus 3 to minus 2 of x squared plus x plus 1 over x dx. Okay, I saw in the last tutorial test, students were finding the antiderivative of the numerator and then the antiderivative of the denominator. Do not do that, it does not work. What you need to do is simplify it into individual terms and then find the antiderivative. So just because it's a fraction doesn't mean you can treat the top and the bottom separately. So here we need to divide through. So we have the integral from minus 3 to minus 2. X squared over x is x over x is 1 over x is 1 over x. Okay, please do not treat it as numerator and denominator separately. Okay, now we've got individual terms, we can find the antiderivative. So x, that becomes 1/2 x squared, 1, that just becomes x, 1 over x, that becomes log absolute value x. Please do not forget that. If you put just log x, it's not going to work, because when we substitute these negative values, log of a negative, there's no answer for that. Okay, so please make sure you put your absolute values there. You can only drop the absolute value if you know that the inside part is positive. Here, we know for sure that the inside part is negative, because we can see from the bounds. So we have to put absolute value there. So this goes from minus 3 to minus 2, then we can substitute. So substituting the top, we get 1/2 minus 2 squared, plus minus 2, plus the log of 2. So now I can drop the absolute value, because I took absolute value of minus 2 is 2. Okay, now I can drop it. Before, I couldn't. Okay, minus, and then in brackets, we can substitute the bottom number. So that will be 1/2 minus 3 squared, plus minus 3, plus the log of 3. Again, now I can drop the absolute value, because I took absolute value of minus 3, which is 3. That's positive, so that's fine. If you want to continue with putting the absolute value, that's fine as well. It doesn't hurt to keep it, but just know that we can drop it at that point. Okay, and then after this point, again, you just simplify. Okay, any questions on this one? Okay, again, when you have that fraction there, please do not treat the numerator and the denominator separately. Okay, you split it up as much as you can, and then you look at each term individually. Okay, number 5. So we have the integral from 2 to 3, 1 over x minus 1 dx. So whenever we have something, yeah. Sorry, x squared. If it was x squared here. Yeah, so if it's x squared there, you continue as we did here. So x squared over x, that would be 1. X over x squared, that would be 1 over x. And then 1 over x squared, we can write that as x to the minus 2. Okay, so it doesn't matter what power it is, you always divide term by term. Okay. Okay, so here, let's go back here. So here we can't split it up. So 1 over x minus 1, we can't write it as two different terms because the sum is in the denominator. So we can't split it up. But what we can do is ignore the minus 1 and that looks like something we've had before. So the antiderivative of 1 over x, that's the natural log. If we put the minus 1, we get something quite similar. So just on the side, a little note. D by dx of the natural log of x minus 1, that's going to be 1 over x minus 1. Okay, so we can add any constant, and if we take the derivative of the natural log, that term in the brackets just goes to the bottom. The only time we don't get that is if we have to then do the chain rule. So if it's like the natural log of x minus x squared, for example, then we would have 1 over x minus x squared, but then we would have to do the chain rule, and that messes it up. But here, if we have x plus b for some constant, taking the derivative just gives us 1 over x plus b. So here, 1 over x minus 1, looking at the side there, if we go backwards and find the antiderivative, it's just the natural log of x minus 1. Okay, so you can add that to your table of antiderivatives. If you have 1 over x plus b for some constant b, the antiderivative will be the natural log of x plus b. Okay, so you can add that to your list there. So here will be the natural log of x minus 1. Okay, from 2 to 3. So here we get the natural log of 3 minus 1, so that's 2, minus the natural log of 2 minus 1, the natural log of 2 minus 1, that's 1, but the natural log of 1, that's 0, so we just have the natural log of 2. Okay, so please include that in that table. Okay, so it's a little extra bit that you can use. Okay, so anything that looks like 1 over x, we're going to be using the natural log. Okay, later on we'll look at 1 over ax plus b, so something a bit more complicated. If you have a coefficient in front of the x, it's a bit more complicated than that, but it's the same idea. It will be the natural log with a little bit added on. Okay, but for now you can just add this to your list. Okay, any questions on this? Okay, next one, number 6. So we have the integral from minus 2 to 2, absolute value of x dx. Now, whenever you have a symmetric bounds like this, so you're going from minus 2 to 2, or minus pi to pi, or minus a to a, whenever you have something like that, the first thing you should check is if your inside function there is even or odd. Okay, the reason is, if it's an odd function, then the answer is automatically 0. If it's an even function, then we can simplify it a bit. So let's check. So absolute value of x. If we put in minus x, that just gives us absolute value of x, which means absolute value of minus x is equal to the absolute value of x, which makes it even. If it's even, we can replace this with twice the integral from 0 to 2. So this is going to be twice the integral from 0 to 2, absolute value of x dx, since the absolute value of x is even. Okay, you can do a little bit of working on the side to check that if you want. Now, if we're going from 0 to 2, x is always positive. If you're going from minus 2 to 2, sometimes it's negative, sometimes it's positive. But here it's always positive. So the absolute value of something positive is just that number. We don't have to do anything. So we can drop the absolute value. Okay. Does everyone understand that? Okay. Now this is something we've just seen before. Okay, we can do the antiderivative. So this will be twice 1/2 x squared from 0 to 2. Okay, 2 squared, that's going to be 4. Divide by 2, there'll be 2. Times the 2 in front, we get back to 4. If we substitute 0, that just gives us 0, so we don't have to worry about that. Okay, so again, if you have a symmetric domain, so minus 2 to 2, minus pi to pi, anything like that, check if it's even, then you know what to do. Check if it's odd, you do something else. Okay, we'll see that in this question 7. Okay, so number 7, we have the integral from minus pi to pi, x squared sine x dx. Again, symmetric domain. It's from minus pi to pi. So it's something like minus a to a. So we look at the inside part and we check. Is it even? Is it odd? So check. So f of x, I'm just calling it f there. So x squared sine x. What about f of minus x? That will be minus x squared sine of minus x. Minus x squared, that's just going to be x squared. Sine of minus x is minus sine of x, so we get a minus in front. But if we ignore the minus, we get back to f of x, so that right-hand side becomes minus f of x, which means it's odd. Whenever you have f of minus x being equal to minus f of x, it's odd. If you have the integral over a symmetric domain of an odd function, the answer is just 0. Okay, no extra work required. But you do need to check. Okay, so please check first if it's even or odd. If it's even, then the most we can do is have that twice the integral from 0 to a. Okay, but if it's odd, it's 0. Yes? Yes, so if you can sketch it, then you can do that. That's fine as well. If it's something more complicated than this, then you can also check like this. Okay, yeah, I did see your sketch. That was fine. So if you can sketch it, that's fine as well, or you can do this. Okay, both are acceptable. But you do need to show your working. You can't just say it's odd without showing me that it's odd. Okay, but yeah, sketches are fine. Any other questions? Okay, number 8. So we have the integral from 0 to 1, 2 over 1 plus x squared dx. Now, just written like this, we don't know what the antiderivative is. Okay, 2 over 1 plus x squared, we haven't seen that before. But we know from our definite integral properties that the 2 can be taken outside because it's a constant. So we can take the 2 out. And then we have 1 over 1 plus x squared. Now, we have seen this before. 1 over 1 plus x squared, that was the derivative of arctan. Okay? We did that with the derivative of arcsine, arccos, arctan. We did those 3. So if the derivative of arctan is 1 over 1 plus x squared, then the antiderivative of 1 over 1 plus x squared must be arctan. It always goes back and forth. So we know the answer already. Okay, so this will be 2 arctan from 0 to 1. If you don't like writing it like that, you can write it as arctan, like this. Okay, both are fine. If that minus 1 messes you up, then you can write it out like arctan. Okay, but both are fine. Okay, so this will be 2 times. Arctan at 1, you just need to think a bit backwards. We know that tan of pi over 4 is 1. So arctan of 1 is pi over 4. Okay, we just go backwards like that. So arctan of 1 minus arctan of 0. Again, just thinking backwards there. Tan of pi over 4 is 1. Arctan of 1 is pi over 4. Okay, and then for the 0, tan of 0 is 0. So arctan of 0 is 0. Again, goes back and forth. 2 times pi over 4, that's pi over 2. Okay. So if you do have constants in your integral there, you can take the constants out. Okay, that's one of the properties that we learned. So here, 2 over 1 plus x squared, we don't know what that antiderivative is. If we take the 2 out, we get 1 over 1 plus x squared. We have seen that before. Okay, so sometimes taking the constants out makes it a bit clearer with what we're working with. Okay, any questions on that? Okay, number 9. Okay, so here we have the integral from 2 to 3, 1 minus x squared over 1 plus x dx. So this is called a rational function. You've got a polynomial at the top, polynomial at the bottom. To solve these in general, we're only going to be looking at that next year. But for now, we can look at this and try and simplify. Okay, so the general case we'll look at later. But for now, there must be some trick that we can use. If we have 1 minus x squared, that's a difference of 2 squares. The 1 we could write as 1 squared. So it's 1 squared minus x squared. So we can write it as 1 plus x, 1 minus x. But notice that one of those terms automatically cancels the thing at the bottom. So please look, if you can factor something, it might be able to cancel something else. So we have the integral from 2 to 3, 1 plus x, 1 minus x, over 1 plus x. The 1 plus x, that can go now. So we're just left with 1 minus x after cancelling. So at the beginning, it was a complicated rational function, but we saw there was a difference of squares, and that cancelled quite nicely. So we're left with 1 minus x. And this is quite easy to do. So this is going to be x minus 1/2 x squared from 2 to 3. Substitute the top. So 3 minus 1/2 3 squared. Substitute the bottom, 2 minus 1/2 2 squared. Okay, and then you can simplify that. Okay, so key thing to take away here, if you can factor something, do it. It might cancel something in the numerator with something in the denominator. Okay. So in this case, we couldn't have the numerator, back here. So here, this numerator and the denominator, we can't write it as separate terms. That doesn't help so much, but we can factor. Okay, so sometimes we can write it as separate terms, like in that previous example, number 4. Sometimes we can factor it to make it easier. It's good to know multiple things to try. Okay, last one, number 10. Okay, we have the integral from 0 to 1, square root x, square root x. Okay, so this might look a bit complicated, but whenever you see square root, think x to the half. As soon as you think x to the half, now it just becomes work with exponents. So this will be integral from 0 to 1, x times x to the half. I just replaced that inner root with the half power, and then everything else is to the half. So this will be integral from 0 to 1. That first x is a x to the 1, so we'll have x to the 3 over 2 inside. And then we still have half on the outside. Now, if we have exponents to another exponent, we multiply the exponents. So 3 over 2, and then the half on the outside, that now becomes 3 over 4 on the inside. And now we can treat this as any other power rule. We add 1 and then divide. If we add 1, that's the same thing as adding 4 over 4. So that becomes 7 over 4. If we divide by 7 over 4, that's multiplying by 4 over 7. From 0 to 1. If we substitute 1, then we just get 4 over 7. If we substitute 0, we get 0. So we just get 4 over 7. Okay, so whatever roots you're given, square roots, cube roots, fifth roots, anything like that, immediately write it as an exponent, and then it's just exponent rules. Okay. And if you have nested ones, like root of a root, then it becomes half to the half, and then that just multiplies down. Okay. Any questions on these 10? Okay, so this is the level of difficulty that you should expect for the next assessments coming up. So the quiz tomorrow and the class test and the final test. Okay, So it won't be as easy as what we covered on Monday. It will be more like this. Okay, but it will be a mix, right? So it won't be all difficult ones. It will be, some of the stuff we did on Monday, some of the stuff we did today. Okay, but you should be comfortable with all of these at the end of today. Okay, any questions before we move on? Okay, so let's have a look at the next set. Okay, so here is FTC 2 or FTC 1 if you're looking somewhere else, but in our notes we called it FTC 2. Got another 10, please find the derivatives. Okay, same rules as before. First person to get the right answer gets the points. Okay, you can do one at a time and show me, or you can do a bunch at a time and then I'll check that. Okay, but you'll have until close to the end of the lecture because I still want to go through the solutions.